Now, after defining sample space, which is capital omega, and the sigma algebra on it, which is F, we move to the third component of the probability space, which is probability measure. So goal here is that once we have the set of all outcomes and we have defined a nice list of all the events we are interested in. Now we will assign some probability to every event, and that will tell the probability or the chance of happening of that particular event. Okay, and now this, why we call it measure, because it is like a measurement of the event. If the event has a higher probability, it means the event has a higher size, right? That is what in this way it can be understood, right? So formally define it, we will first talk about what a measure is, and then we will talk about what is probability measure is, and then things will become little bit easier to understand. So what is a measure? So measure is a simple function which assigns size to each set. Okay, so what sets? So that is why we have a collection C. This collection is a collection of sets. Okay, so we have fixed that. Now we will say we want to define a measure on this C for this collection. It means I want to define the size of each set. Okay, what do you mean by, what do we mean by size? Size can be anything, right? Uh, let's take this particular example. Here is a collection of classroom. Okay, each member of this collection is a classroom. So you can think is the lecture hall 1, lecture hall 2, lecture hall 3, or you can think about from the course perspective. This is course 1, this is course 2, course 3. Okay, and then when you collect them, this is a collection. Now I will say, can we assign a measure to this class? So one measure can be how many students are there in each class. Okay, so a small class would be where there are less students. A big class would be where there are more students, right? So this measure gives also a sense of size of that each set. Okay, and we can tell which is a small set, which is a bigger set. We can compare the size of two sets. Okay, we can have another measures also for the same collection. We can say that instead of students, I would look at the floor area of each class, and then I will say the size of this class is the floor area, or anything you can assign, number of fans in it, number of instructors for each class, number of TAs for each class, and that will be a measure. What other examples of measure we have seen? Length is a measure, right? So if you have a collection of line segments, right? So each member is a line segment, and line segment itself is a set. So when I talk about the size of this set, it will be just the length of the line. For two-dimensional objects, a collection of some triangles, the area can be a measure. Okay, therefore collection of 3D objects, the volume can be a measure. Okay, so these are the kind of measures we can have, right? For the same collection also, we can have different types of many measures, right? So formally, if I define it, if I have a collection C, a function mu from domain collection of C to a real positive number, including 0, this function would be a measure on C. Okay, it takes each element in C and assign a number which can be positive or 0 also. Okay, we do not include negative because the size we assume cannot be negative. So minimum size can be 0 or a positive number. Okay, and the whole theory which deals with such kind of functions comes under measure theory. It's a different branch, and itself there are courses on it which you can learn. In this course, I am going to talk about relevant things which would be important to understand the probability space. Okay, So there are some properties of this measure. Any function from C to R plus cannot be a measure. There are some things, some condition which will make sure that this looks like the size of a set. Okay, so formally, if we want to write it, the measure is defined in the following way. I'll talk about the mathematical definition first, and then we will understand each part of it. Let X be some set. So first you have a set X. Then F be a sigma algebra on an X. Okay. So this will define a collection of subsets of X. Okay. So my goal is to define the size of each subset or some subsets of X. So for that, first I made a list of all subsets of X in which I would be interested in. Okay, and that will be in sigma algebra. Now I say I will define a function mu which will be from F to R plus including 0. This will be a measure if it satisfies three qualities. Okay, first is the mu phi is equal to 0. Right? So if you apply this function to a null set, it should be 0. Right? Now you can understand one more point, that mu is defined on F. Okay, so it is only defined for the elements in F. Okay, and to say that mu phi is 0, you need to make sure that mu is defined for phi. Right, and that is there because phi is in the F. Okay, by definition, F is a sigma algebra, so this empty set should be a member of F. So that is why mu phi is defined, and mu phi should be 0. Similarly, for any set E in F, mu E should be greater than or equal to 0. This just means that size cannot be negative. And the third property, which is important, is if there are n sets a1, a2, an, and they are disjoint, then the size of the union of this set, okay, the measure mu of the union of this set should be equal to the summation of the size of each set. Okay, summation of the measure of each set. And this is also true for countable number of sets, not just finite sets. So if I take a1, a2, an up to infinite, infinite sequence of disjoint sets, then also this is true that the union of the size, the size of the union of sets should be equal to the summation of the size of individual sets. Okay, so in simple words, it means that if you see this rectangle, orange rectangle, if you divide into two parts, disjoint parts, then the size of the original rectangle should be equal to size of summation of the size of these two individuals. Okay, and that's a very intuitive thing about measures, right? A size. Length also, if you take a line, break into two parts, the length of the summation of the length of two parts should be equal to the length of the complete line. Okay, so there is a nice property of this union that when you break a set into two parts, the total size should not change. Also, if you merge two parts, disjoint parts, the total size of these two parts should not change. Okay, so that is what a size, volume, and this is a fundamental law, right? That the volume, area, and they should not change. Okay, so that is where this formula comes from. It is intuitive from the definition of a size. Okay, if you divide a line into two parts, the area of these two parts does not change in summation. Okay, so once we have this measure, I will say X, F, and mu is a measure space. Okay, this collection of these three objects, where first is the set, second is a sigma algebra on this set, and the third is a measure on X, then this is called totally a measure space. And once you have defined a measure, then all the members of F are called measurable sets because you have defined their measure. So if there is an element in F, it means you know what is the measure of it. You just apply mu to it, and because mu is from C to for F to R plus, that's why it's a function. So it needs to be defined for every member of F. Okay, so if you take any element in F, the measure need to be defined, and once we know the measure of it, we say the set is measurable because we can know the measure of the set. Okay, so this was measure, right? Now the thing is, what is probability measure? So probability measure is a measure with a slight change. So let me formally define it. A function measure P from F to 0, 1, and F is a sigma algebra, is a probability measure if, so now to notice here is, instead of the complete real line, positive real line with including 0, I have only included closed set 0 to 1. Okay, closed set means it is a set containing all the points between 0 to 1 and including the boundaries 0 and 1. Okay, so the value can be the function value, the measure value would be between 0 to 1, including 0 and 1. So P is a probability measure if probability of phi is 0, that is same as measure. Probability of capital omega is 1. It means the probability of the complete space, complete sample space should be 1. Okay, that is also intuitive because if you have all the outcomes, one of them need to happen. So the probability that one of the outcome happens is 1. It is an exhaustive list of outcomes. And the third property is the same. It is that if you take two disjoint sets of omega, the probability measure of the union of these sets is equal to the summation of the weighting. Okay, but in the property we write in a general form, we say if you take a countable number of sets, an infinite sequence of disjoint sets of omega, then your probability of this countable union of AI is equal to summation of probability of each individual sets. Okay, and then of course I will say omega, which is x. Set is omega, capital omega. Sigma algebra is f, and the p is the probability measure. So I say omega, f, and p. It's a probability measure space. Okay, or a probability space, and all the sets in F are now measurable sets. Okay, these three properties are, or axioms, are known as probability axioms. Okay, and which make the basis of the complete probability theory. Okay, so what is different here than the measure? Only thing is, in the second property we have P omega is 1. Okay, and that just tells us that the maximum value can be 1 because the biggest set is omega. Okay, of all the subsets of omega, the biggest set is omega. Okay, and the size of it is 1. So that is the maximum size you can assign. Okay. From this property, it is not immediately clear to some of us is why the bigger set has a bigger measure. Okay. Why I say that if there is a subset of omega, then it should have a measure value less than measure of omega. Okay. So we will show later on, discuss the properties of probability space. From this, it will become more and more clear that this probability measure is a monotonic function of the size of the set. Okay, if something is a subset, if A is a subset of B, then probability of A should be less than or equal to probability of B. Okay, such kind of things, a nice thing we can see. So eventually what you get is that the maximum size of probability measure of any set can be 1. That is why this probability measure is between 0 to 1. Okay, and minimum value is already 0 because of the measure definition. So in the last class, we talked about probability measure. We have defined it using three properties. We said a function from sigma algebra to 0, 1 is a probability measure if the P of phi is 0. It means it assigns size 0 to a empty set. P of sigma is 1. It means it assigns size to the complete sample space as to 1. This is the maximum value of the function. probability measure. And then we said that if you take infinite countable sets, disjoint sets, A1, A2, A3 up to A infinity, then you can say the probability of the union of these sets is equal to the summation of the individual probabilities. And these are known as probability axioms. We show that although we only have to prove these three properties to say some thing is a measure, the probability measure itself comes with other properties also, which just follow from these three properties. So we will discuss some of these properties as they will be useful in the later computations. First is the countable union. Uh, we already know that the if you take the infinite number of sets, a countable number of sets, then the probability of union is equal to summation of the individual probability of individual sets. But this is also true for the finite union also, not just the countable union. This means that if you take some n sets a1, a2 up to an, then also, and they are of course disjoint, then also the probability of union of these n sets is equal to summation of p of individual sets. Okay, and this is true for any n. In particular, when n is equal to 2, if you take two sets A1 or A2 or A and B, and of course you have to make sure they are disjoint. So A intersection B is pi. Then also you can say the probability of A union B is equal to probability of A plus probability of B. Okay, and this is similar to the thing we were talking earlier, that if you break a set A union B into two parts, A and B, then also the size should be preserved. So how can we prove this? Right? Proof is little bit involved, uh, although it looks intuitive to us. So let's see how we can prove this. So first, what we'll do, we have only finite number of sets, but the axiom says that the formula we know, it is for uncountable number, sorry, it's for countable infinite number of sets. So what we do is we construct a new sequence, infinite sequence of set Ci, which is made from A1, A2 up to An, and then the rest sets are assigned by 5. Okay, so we can see that it is n sets are a1, a2, an, and the rest sets are we can call them b1, b2, b3 like this, and this complete sequence is ci, and then of course this b1, b2, b3 all are just empty sets. Okay, so why we have taken empty set? So that the union does not change. Okay, we will see in a bit. So just to say it again, the sequence is constructed in a way that Ci is made from A1, A2, An, and then after that it is follows from B1, B2, and Bn. So I is equal to 5 for all I. Now, what we can see here is if you take the union of all this set I, okay, this is the infinite countable union, then this is equal to the union, this is the union of all set Ci's, this is equal to the union of these AIs and then these BIs. Okay, so we can write it as equal to union of AIs and union of BIs. And then union of BI is all are 5, so the union is also 5, right? If you take multiple infinite, doesn't matter, empty sets, there are not a single element in those sets. So the union is also empty. So this is equal to the finite union of sets AIs. So what now we can say that probability of this finite unions of AI is equal to the probability of this countably infinite union of Ci. Why? Because union of AI is equal to union of Ci's, as we just proved. Now, from the axioms, we know that the probability of union of all those Ci's is nothing but the equal to summation of individual probabilities of Ci's. Okay. One thing which need to still prove that these CIs are also disjoint, and that is not difficult because uh, if you take A1 with union with any of the AIs, if CI says that they are less than n, then it will be AI union intersection with any other set. And because AIs are disjoint, so this will be disjoint. If you take union of intersection of any sets in B's, Bi and Bj, then also is phi intersection phi, which is phi itself. And if you also take any intersection between AIs and Bj's, then also you get phi because Bj's are phi. So all Cj, no matter what Ci, Cj you take, the intersection is phi. So these Ci's are also disjoint. So that's why we can say from the axiom that probability of union of Ci's is equal to individual probability C. It's the summation of the individual probability Ci's. Now you can break this into two parts. Again, so Ci's are, as we know, from 1 to n, it is AI, and then after that is Bi. So this summation can be written as summation of P of AIs, up where I is 1 to n, and then I to infinity PBIs. Okay, now if you look at what is a PBI, PBI should be 0 because BI is an empty set. So this means this is summation over all zeros. Okay, summation of all 0 is 0. So you get P of AI is the only term remaining, which is equal to summation of PAI. So what we have proved that the countable finite union of AIs is also, you can say that probability of this union is equal to summation of the individual probabilities of these sets. Now let us see some more properties of probability measures. One is if you take a complement of a set, then you can say that the probability of A complement is equal to 1 minus probability of A, or you can say also probability of A plus probability of A complement is 1. Okay, and how we can prove this? We will use the property we proved in the last class, that if you have two sets A and B which are disjoint, then probability of A union B is equal to probability of A plus probability of B. So here we will take this first set as A and the second set as A complement, and they are disjoint by the definition. So then we can say probability of A1 union A2 is equal to probability of A1 plus probability of A2. Probability of A1 is probability of A, probability of A2 is probability of A complement. So this means probability of A plus probability of A complement is probability of A union A complement. And we know that A union A complement is the complete omega space. Okay, so which probability is 1? So from this we can prove this property. Then we will also show this interesting useful property that if A is a subset of B, then probability of A should be less than or equal to probability of B. This means that if you make a set bigger by adding some components, the probability cannot decrease. Probability will either increase or may remain same if the elements you have added does not have any extra probability assigned to them. Okay, so how can we prove this? So what this is very easy. We will use a similar argument again. So if A is a subset of B, right? It means A should be in B, and there may be some other elements in B which are not in A. But every element in A should be in B. That is the meaning of subset. So in this way, you can write B in two parts. B will be equal to A, and you have to add the rest element which are not in A but in our B. So what are those elements? Those can be either said that B minus A, that will be the element which are in B but not in A. Or another way to write the same set is also B intersection A complement, which means you take all the elements which are in B and you take all elements, you take all elements which are in B and also in A complement. And something is A complement means it is not in A. So you are taking all elements which are in B but not in A. So if you take these two sets A and B intersection A complement, uh, they are disjoint, right? because first set has set elements in A, and the second set has elements which are not in A. So they cannot be any element common. They are disjoint. And also, if you take A and then you take B while removing elements from A, then if you take the union, you will get the complete set B. Okay. So if any element is in B, it will either be in A or it will be in B but not in A, which is the second element, second set. So the union is also B. Okay, this you can also very easily understand from the Venn diagram. If you make a set B and then A, and then you will see A is inside B. So the rest of the B is made from two parts, A, and the rest of the area around A, which is nothing but B intersection A complement. So these are two disjoint sets. So we can apply the property which proved that probability of B should be equal to probability of A plus probability of B intersection A complement. Okay, this is nothing but just saying that probability of two sets A1 union A2 is equal to PA1 plus PA2 if A1 and A2 are disjoint. Okay, now once we get this, you can see this probability of B intersection A complement. This is probability of some set, and the probability of some sets cannot be negative. It will be either equal to or greater than 0. So if you add something in PA which is greater than or equal to 0, you will of course get something which is bigger than PA. Okay, so you can say that PB should be greater than or equal to PA. It cannot be less than it, right? If you add anything to PA, a positive number or even 0, you cannot get a number less than PA. Okay, so that is why how we get this. So it's a nice property that if you add anything in a set A, then to get B, then you cannot decrease, the size cannot decrease. It should either be equal or should increase. Okay. Now we will come to the fourth property, which you may have seen in past. This says that if A and B are not disjoint, then how do I compute A union B? In that case, probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. And this is consistent with the previous result that if A and B are disjoint, then of course A intersection B would be 5. So probability of 5 would be 0. So this will give you the same result that probability of A union B for two disjoint sets is equal to probability of A plus probability of B. But here we have a general result where A and B cannot be disjoint. So how do I prove it? Okay, this can be proven in the same way. First, you can show that A union B is made from two components, A and then B minus A. Okay, this B minus A is a set minus, which means you take B and you remove all the elements which are in also in A, and you keep the rest. That is how you get B minus A. Okay. This is again to say this is B minus A. This minus is a set minus. Okay. Then or we can also write in terms of B intersection A complement. Both are same things. So A union B is nothing but A union B minus A. Okay. So they now A and B minus A are disjoint. So you can say probability of A union B is equal to probability of A plus probability of B minus A. Okay, that is first part. Now we have to prove that probability of B minus A is equal to probability of B minus probability of A intersection B. If we can prove this, then we will just put the result and you will get this final result. So how do I prove that probability of B minus A is equal to probability of B minus probability of A intersection B? Right. That is very easy. That is equivalent of saying that probability of B is equal to probability of A intersection B plus probability of B minus A. Okay. And here you can also say, show this, that A intersection B and B minus A, they are disjoint. Right. Because A intersection B must have elements in A, and B intersection B minus A must have elements that are not in A. So these two sets are disjoint. Now, if you take the union of A intersection B, and B minus A, you will get the set B. Because A intersection B has those elements which are in B and B minus A has those elements which are in B but not in A. If you take the union of these two, you will get this complete set B. So this means probability of B is equal to probability of A intersection B plus probability of B minus A. From this, you can show that probability of B minus A is equal to probability of B minus probability of A intersection B. Okay, and earlier I proved that probability of A union B is equal to probability of A plus probability of B minus A. So I will just put the result of probability of B minus A, and then you will get this expression. Okay, another way to say this also, that probability of A union B plus probability of A intersection B is equal to probability of A plus probability of B. Right, now we come to the fifth property, which we call union bound. This means that for any set A and B, probability of A plus probability of B should be greater than equal to probability of A union B. Okay, and this directly follows from the previous property, where we have shown that probability of A plus probability of B is equal to probability of A union B plus probability of A intersection B. Right. So if you use this, this will be, you can say that probability of A intersection B would be greater than or equal to 0. So in that way, probability of A plus probability of B should be greater than or equal to probability of A intersection B. Okay. And when the equality holds, when probability of A intersection B is 0, which is when A and B are disjoint. So when A and B are disjoint, then they are equal. For other sets, if you add probability of A plus probability of B, you will get more elements, probability of A union B, right? And how does this appear? What is the intuition behind it? So see, if you take two sets, right, and if they are disjoint, the combined size is just the sum of the size. But if you take two sets where there is some intersection, right, if you add them, one intersection is being added twice times. So that is why the summation of this probability will be larger than the overall area, overall size. This union bound you can generalize to more than two sets or even infinite sets, where you can say that if you take a sequence, infinite sequence of sets A1, A2 up to A infinity, then the summation of P of AIs should be greater than equal to probability of this union of all these sets. Okay, and remember the left hand side is just a summation of PAs, and this is true for any AI. So it may happen that if you take some specific AIs, this summation will become infinite, okay, or even larger than 1, right? So in that case, if the summation is larger than 1, then of course it will be greater than any probability. So it becomes not that much useful. In this case, sometimes we add one more condition, that if PII is greater than 1, then we just say that replace it by 1. So we take minimum of these two should be greater than probability of union of A. Okay, so this kind of bounds are used to put a bound on the union of some sets. Okay, so this says that if you take some sets, the union, so probability of the union of these sets cannot be more than the summation of the probability of individual sets. Okay, and of course, if the summation is more than 1, then we just say that this probability of this union should be less than 1. Okay, because using the summation form is no longer useful, because we know that probability cannot be more than 1. Right, so we have a better bound than just using the summation. Okay, now we come to the property which is a asymptotic, a limiting kind of property, which says that if you take sets AI and take the union of these sets. Okay, again, just to recall, this is not a one by one infinite union. This is a union of AI where I is 1 to infinity. It means that this is made from taking elements from all AIs. Okay, So all the elements which at least exist in one of the AIs will be in this set. Okay, so that is all we have to say here. So here we can say that probability of this countable infinite union of AI is equal to limit of n tending to infinity of the probability of this finite union of AIs. Okay, so if someone wants to compute this infinite union of AI, he can just take first n sets, take it union, is compute probability, and then it increase n one by one, compute the probability, and he will get this limit as the complete probability. Okay, so just remember that applying the limit on the left hand side is not possible because it is not defined how you take the limit on the sets. You cannot say that limit n tends to infinity union of AI where I is 1 to n. Right? That is not defined because the limiting limits of sets is not defined. Okay, but probability of union of AI is a number. So you that changes with n. That is a real number. That is a real sequence. So a limit is defined in general that something converges to a value if the distance is decreasing. Okay, you can look at the definition of convergence and limits if you have any confusion. So how do I show this? So first of all, we will notice that this involves a union of sets, and the result of equality where we know is for only defined for sets which are disjoint. So let me construct a sequence of sets such that the union still remains same. Okay, but these new sets are disjoint. So what I will say is let me construct BIs in the following way, such that B1 is A1 and B2 is A2 minus A1. Okay, and then B3 is A3 minus A1 union A2. So this means B1 is made from sets elements of A1, B2 is made from elements of A2, but not after removing the elements of A1. Similarly, B3 is made from elements of A3 after removing the elements which are either in A1 or A2. Okay, so if you like write like this, you can show that this B1 and B2 are disjoint because if let's take B3, a B3 has elements which are in A3 but not in A1 and A2. Okay, and if you take it intersection with B2, B2 only has elements which are in A2 slash A1. Okay, so B3 and B2 will be disjoint. Right. So now once we have got this sequence of disjoint sets, right? Now and then union is same, right? Because if you look at here, we are not leaving any elements of union of AI, right? This we can actually formally prove that the infinite union of BIs is equal to infinite union of AI, right? So how do we prove that these two are equal? To show that uh, to show for any set E is equal to F, what you need to show that if there is an element in E, it need to be in F, and if X is an element in F, it need to be in E also. Okay, if you can prove this two statement, then you can prove E is in F. Okay, so can we show this for this? If an element is in union of BIs, then it should be in one of the set BIs. Okay, so let's assume the first, it can be in multiple sets, but let's assume the first set, first BI, where it is BI, suppose, right? So BI means should be in AI, but it is not in uh, any sets prior to that. Okay, so if it is in AIs, then of course it will be also in the union of AIs because union of AI is made from all elements of AI. So if something is an AI, it should also be in the union of AI. Right? That is one side. Now for the other side, I have to prove if something is in union of AI, it should be in the union of BI. So if an element is in AI, it need to be in one of the AIs. Okay. If it is in AI, right, it need to be either in BI or one of the sets before that. Okay, so by this argument, you can prove that the countable infinite union of Bi is equal to countable infinite union of Ais. Okay. Similarly, you can also prove this for the finite union also. You can prove that for I equal to 1 to n, this finite union of Bi is equal to the finite union of Ais. Okay, by the same argument. So using this, now we will apply the third axioms of probability, which says that probability of union of AI, first I will convert it to probability of union of BI, right? By using the fact that union of AI is nothing but equal to probability of union of BI. Now I will apply the probability third axiom where it says the probability of uh, countably infinite union of disjoint sets is equal to summation of probability of individual sets. So this will be equal to summation of PBI. Okay. Now from using the limit argument, we know that the summation of a sequence, a summation of a series is equal nothing but if you take an element and compute its sequence, and if you take n to infinity, that will be just equal to that. Okay, that is the definition of the uh, series summation. So this will be equal to limit of n tending to infinity summation of PBI. Okay, and from this we know that summation of PBI is nothing but the probability of union of uh, BIs. Okay, this we have proved as property 1, the finite union of disjoint sets. Now we know that union of these BIs are nothing but the union of AIs. So this we finally proved that the probability of infinite union of AI is nothing but the limit n tending to infinity probability of the finite union of first n terms of AI. Okay, how does we prove that this limit exists? This is very easy. This probability is bounded because it's less than 1, and it is increasing as you take one more and goes from n to n plus 1. You are adding one more term, ai plus 1. So when you are adding something, it is monotonically increasing. So a monotonically increasing and bounded uh, sequence always converges. So the limit exists. Okay, as a special case, you can take a particular set A1, A2, A3 such that A1 is subset of A2 and subset of A3, right? So these sets are monotonically increasing such that the previous set is contained in the new set. So in that case, you will see that the finite union of first A terms and terms is nothing but the last AN term, right? For example, if A1 is inside A2, then A1 union A2 is A2, right? So then I can replace this finite union just by an. So I can say the probability of the infinite union of AIs is nothing but limit n tending to infinity probability of an. Probability space can be categorized into two spatial classes. One is discrete probability space, another is continuous probability space. And there will be slightly difference in how we treat these two probability spaces in terms of calculations. So let us discuss them one by one. So first is the discrete probability space. So the definition according to definition says a probability space omega fp is said to be discrete if omega is finite or countably infinite. Okay, so this means if a sample space is either it has finite number of outcomes or it has a countably infinite number of outcomes, both ways the probability space will be called discrete. Okay, so what is the reason behind it? In this case, assigning probability measure is very easy. What we can do is we can just make singleton events, and we will be able to assign probability measures to every singleton events. Okay, and we can show that by using this we can assign it to all subsets of omega. So in that case, because we will be able to assign for all subsets of omega, we can just take the power sets of omega as sigma algebra. Okay, we can of course take a smaller set as a sigma algebra, but we can also take just the which is a power set which is the largest sigma algebra, and even in that case, we can assign the probability measure to each singleton event and each set in sigma algebra. So let us take first when sigma omega is finite. And in that case, you can take power set as the complete sigma algebra, which power set will also be finite, or we can also take a smaller sigma algebra. Both cases, we will see an example how we can assign probability measure. Okay, so you need three things to complete the probability space: omega, f, and p. Okay, so omega is given to us. Omega is finite. Then we have to construct F, which will be constructed based on what are the interesting events. And you can take power set as a sigma algebra, or you can take a even smaller set, a sigma algebra. And the third thing would be how to assign probability measure. Okay. And remember, probability measure is a function on F2, 0, 1. So it need to be defined for every element of F. Okay, so then only you can say I have defined probability measure only when you have defined it for every element of F. Okay, and this F is every element of F, and of course these elements of F are nothing but the subsets of omega. And how many subsets you will take, that depends on how what is your sigma algebra. And once you have defined P also, then we will say the complete definition of probability space is done. So let's take one example. What if we take a smaller sigma algebra, which is only made from phi and omega? This is sigma algebra. We have already shown that it satisfied all properties of sigma algebra. In that case, you have only two elements of F. Okay, and what will be to assign probability measure? We have to assign probability measure to every element of F, and there are only two elements. And even there is nothing to do here, because we already know that the probability of phi should be 0 and probability of omega should be 1. Right? That is by definition of probability measure. There is no ambiguity here. So we can say probability of phi is 0 and probability of omega is 1. And these are the probability measure definition. I have defined it for both elements of F. There is nothing else to define. So we have defined omega, f, and p both. So this omega, f, and p will make the probability space. What if we take another sigma algebra which is made from, suppose our omega is ht, then our f would be omega, h, t, and ht. This is the power set of omega. I have taken the largest sigma algebra possible. In that case, what we can do is we can start with phi. Probability of phi should be 0. Then we have to assign probability of h and probability of t, and then probability of ht. We know that probability of ht is 1 because that is complete omega. So now let us start with probability of h. So if we define probability of h equal to p, then probability of t need to be 1 minus p, because probability of ht is equal to probability of h plus probability of t because of disjoint behavior. So if one is p, the other need to be 1 minus p, so that the summation is 1. Another way you can look at is the set t is complement of set h. So probability of t should be equal to probability of 1 minus probability of h. Okay, and again remember, I am not defining the probability to h or t. I am defining probability to events. What is the event? The set h, which is a singleton event which contains only one outcome. I am assigning probability to that event. Okay, I am assigning probability to singleton event of t. I am also assigning probability of event of which has both h and t. Okay, but in the notation is important. We are not saying this probability of h or probability of t. We are saying probability of set containing h. So this probability is defined in F. So it need to be defined on every member of F. Outcomes are not elements of F, but the events are the members of F. Okay, so just remember this. This is a convention we took, and it will be important as we move ahead. Okay, so let's take one more example. So in this case, it is clear that if we define the probability of all singleton type events, then defining the rest would be easier. Okay, just to see it clearly, let us take a bigger example, because these two examples were very small. So let's take a example where we flip a coin 5 times. Okay, and we do it until we get a head or number of tosses exceeds 5. If we do not get head, even after 5 coin tosses, we just stop. So in that case, my omega is made from these events, because once we get a head, we stop. So the outcome can be H, because if you get first H, then you do not do any other coin tosses. Or the outcome can be TH, which means first is tail, then you do one more flip and then you get a head. Similarly, you can have other outcome can be TTH, 3TH, 4TH and all 5T, where you do not get a head even in the uh, last step. Okay, so this is my omega, and if you can check that all the outcomes are covered. Now when I define sigma algebra, let us take I am interested in all those events. So I define F as a power set of omega. Okay. So there are 5 elements in omega, so there will be many elements in F. And we have to assign probability to every element of F. So how can we do this? We will see that if we can just define the probability to all singleton events, right, which contains one outcome, then the rest is automatically defined. So how we can do this? Let's assume probability of E1, which is probability of set H, is half. These are arbitrary, right? So what you have to do is you have to do these experiments. You can estimate the probability and then write this way. But here I'm interested in more like a mathematical object, right? How we can assign. What we can assign, that's a second step, right? I just want to make sure that if you are given any examples, you will be able to assign this probabilities. These numbers does not matter for now. I just want to make it that this is a valid probability measure, it is consistent, and I am able to define for every element of F. So then probability of E2 is probability of set TH is, let's say it's 1 by 4. Probability of E3 is 1 by 8. Probability of E4 is 1 by 16. Probability of E5 is 1 by 32. And probability of E6, which is all T, is E by 32. Okay. So let's consider these are only 6 elements, while F contains all subsets of E. Okay. All subsets of omega. Any event E in F would be a subset of capital omega. So it will be made from the outcomes of E, outcomes of omega. So it will be a union of few of these elements, right? You can take a minute to convince yourself that any element E in F would be nothing but just the union of some of these events. Okay, let's assume you take a set of omega which is H and 2TH. Okay, so this will be this H and this TTH. So the union of these two, even union E3, right? So the same set H comma TTH can be written as even union E3. So you take any set in omega, and this can be written as a union of these EIs. Okay, so then we can say that if you have this E and you want to calculate this probability, you just take the individual probabilities of the sets which are making this set. So in this case, as I said, the E I have taken is made from E1 and E3. So probability of this set will be nothing but the probability of E1 plus probability of E3, which is half plus 1 by 8. Okay. So mathematically, I can write is probability of E is summation over all i's. You take P probability of that EI, and then you multiply by 1 if EI is a subset of E. It means if E contains that EI, EI has a singleton event. So this means if E contains that singleton event in EI, then you add that probability of EI. And if it does not, you do not add. So if there is a E which is made from E1, E4 and E6, you just add the probabilities corresponding to these three, and that will be the probability of set E. Okay, and as I said, every event will be covered by it, And what will about the probability of omega? Probability of omega is made from union of all these sets. And if I add them, they are 1. So probability of omega is 1, which is consistent. Okay. So the question is this a probability measure, right? So you can try and convince yourself that it satisfies all the probabilities of all the properties of the probability measure. Definition along with this 6 values is a sufficient definition to assign probability measures on every element of. We'll move to countably infinite sample space. So discrete probability space, the omega can be either finite or countable infinite. So in this case, we will take an example where sample space is countable infinite. So what is the benefit we get when we say countable? It means is a bijection from natural numbers. So you will be able to order all those outcomes in omega, okay? Because omega is countable. So you will be able to say which is the first element, which is the second element, the third element. So from this definition, there will be 1, omega 2, omega 3 like this, okay? This order comes because of the countability assumption. Similarly, we can also define EIs, which are singleton events containing omega i's. And because omega i's are ordered, so EIs are also ordered. Right. So once we have this ordering, we can assign probability to this EIs. Right. So this countability and ordering gives us a nice property that you can take elements one by one and assign the probabilities to it. If this is not countable, then if I ask you to assign probability to each event, it cannot be done by picking numbers in order one by one, right? Because that no order exists. But because of countability assumption, this is a nice list of events, EIs, elements one by I equal to 1, I equal to 2, I equal to 3, and you keep on assigning some numbers to it, right? So what will I assign? Let's assume there is a sequence of real positive numbers, AIs, such that the summation is 1, right? So there are multiple examples of such sequences. One example can be half, 1 by 4, 1 by 8, up to 1 upon 2 to power I, right? This is a sequence which is infinite. It's a real positive number and it adds to 1. Okay, so we can just take this sequence or any sequence which adds to 1, and then first element is assigned to A1, second element's probability is assigned to A2, like this. Okay, and of course we will also assign P5 equal to 0. Now these are I have only defined up to the singleton events. What about the rest events in sigma algebra? Right? Here also I am assuming sigma algebra to be the power set of omega. So there are many elements in sigma algebra, right? But we can recall that any element, if you take in F, is just a subset of omega, okay? And it will be made of the different outcomes of omega, okay? So this will be nothing but a union of EIs, some EIs. Okay, sometimes it can be a countable union, sometimes it can be a finite union also, depending on how big E you are taking, right? You can take also for example, you can take union of E2, E4, E6, like all even numbers of events. Okay, in any case, you take any E, it will be a union of EIs, and you can assign the probability of E as summation over all those EIs which for which W omega I is in E. Okay, or you can say omega I is in E means the EI is E contains EIs. EI is a subset of it. They are all same thing because EIs are made by EI is a singular element containing only omega I. So if I say omega I is in E, it means EIs are a subset of E, or E contains that EI. So you will check with every element from going from I to infinity, and you will check which EI is contained in E, or E is made from which EIs, and then you take those events, synchrone events, and add those probabilities. This addition summation would be the probability of E. Okay, now every E it can be constructed this way. So I have assigned probability to every element. Okay, so one step is clear that it's a probability measure in a sense that I have assigned the one number to every element. Now the remaining is to prove that this is a valid probability measure. Right? It means it satisfies all three properties. Right. So phi does not contain any EI. So I have already said it is equal to 0. Then omega contains all EIs. So if I add all EIs, I should get 1 because I have taken AI such that summation AI is 1. Okay, so two conditions are true. Also, you can show that if you take a smaller subset of omega, then the summation will be less than 1 because you are missing out some EIs. And then the third axiom you have to prove, right? So this just says that P phi is 0 by definition, P omega is 1 because P omega is nothing but union of all EIs, so you have to add all PI which are 1. For third, you have to do some work. We will show for a one example when n is equal to 2. So let's assume there are two sets, A1 and A2. Then we have to show that by the definition of probability measure we have taken, probability of A union A2 should be equal to probability of A1 plus A2 if A1 and A2 are disjoint. Okay, let's assume A1 and A2 both are countably infinite. Then again, because see, omega is countably infinite, so all subsets of omega need to be either countably infinite or finite. Okay, let's assume they are countably infinite. Then A1 is made from an ordered list of events, right? Let's call it omega I1, omega I2, omega I3. Similarly, A2 is also made from an ordered list of outcomes, which is made from omega G1, omega G2, omega G3. Okay, now you can say the union of A1 and U2 is a combination of the union of these two. Okay, and the way I'm doing this union is I'm taking one element of A1 and then one element of A2 and one element of A1 and then one element of A2. Okay, I can take any order, doesn't matter. It's the union, it contains all elements of A1 and A2. Okay, so if you write this way, then this will be nothing. A1 union A2 is nothing but probability of omega I1, omega J1, omega I2, omega J2 like this. Okay, now we can say this is nothing but this set is nothing but the union of EI1, EI2, EI3 and EJ1, EJ2 and EJ3 like this. Okay, so now I can, this is just a sequence, I can break this summation into two parts. One would be summation of all terms of EI and another would be all terms of EJs. So this will be summation of PIK, EIK and then summation over EJN. Okay, where you are changing from K1 to 1, so it will be EI1, EI2, EI3 and then if you change N from 1 to infinity, it will be EJ1, EJ2, EJ3. Okay, now what is probability of EIK? This is probability of EIK is by definition is the probability of union of all EIKs. Okay, and probability of union of all EIKs is nothing but A1, right? So A1 is made from all those events omega I1, omega I2, omega I3, so which are corresponding to events EI1, EI2, EI3. So if you take union of these sets, you will get A1. So the first term is nothing but the probability of union of EIKs, which is nothing but probability of A1. Similar second term is probability of A2. So that this will be equal to probability of A1 and probability of A2. Okay, if one of them is a finite set, then of course you can prove this by replacing the rest term as a phi. Okay, so this you have to prove for not just n equal to 2, this you have to prove for any n. Okay, but it can be shown that countable union of, I think it was in one of the assignment, that countable union of countable sets are also countable, right? So from that argument, you can again create an order of this countable union sets, and then you would be able to prove this. Okay, so this is the way we can assign the probabilities. Now the remaining term is what we can assign. So this sequence of AIs, that depends on your experiment. So you have to do the experiment or some kind of reasoning, physical phenomena you have to understand to be able to assign what number I want to assign to which event. Okay, and that if you want to relate to the physical world, it need to show this numbers need to represent the probability or the chances of that event happening. But as far as math is concerned, we don't care what number you will assign. You just have to assign so that it becomes a valid probability measure. Okay, and of course you can understand if there are two different scenarios where the same outcome probability changes, then the probability measure would be different for those outcomes. Okay. So now let's come to one example. So let's see, we consider a finite coin toss experiment in which we toss the coin until we get a head. So the sample space, see earlier we were taking just 5 coin tosses. Here is an infinite coin toss experiment. So the events are like H, TS, TTS, TTS, and it doesn't end, right? It's an infinite coin toss until we get H. So last time, last in any outcome, the last one is head, but the rest before are T. So this is again a countable infinite set, because if you see any element, you can count how many T's are, and that will tell you that if there are 4 T, it is the fifth element. Okay, so the ordering is already defined. Now I can take F as the power set of omega, right? And power set of omega means it contains all subsets. Again, we will do the same thing. We will take the singleton events and assign probability to it. And the rest events can be similarly defined, that if an event contains 5, 6, and 7 outcome, 5, 6, and 7 event corresponding to the singleton events, then you just add the probability of those. Okay, last one example I'll contain. Suppose you have two sample spaces, omega 0 and omega 1, and both are natural numbers, right? Both are countably infinite. So you can take natural numbers, or you can just assume they are countably infinite. There's a mapping between them and natural numbers. Then I want to say that if you construct a new sample space, omega 0 cross omega 1. So this cross means it's made from combination of, it's like a set of pairs where first element is from the first omega 0 and the second element is from the omega 1. Okay, so if omega 0 is ht and omega 1 is also ht, this will be hh, ht, th, and th. 4 elements should be there. So we want to say that if omega 0 and omega 1 both are countably infinite, then omega cross product omega 2 should also be a countable infinite, right? And we can show this by simply saying that there is a bijection between n cross n to n. So it means n cross n is also countably infinite. So similarly, omega 0 cross omega 1 is also a countable event. Okay, so if you construct a sample space by taking the Cartesian product of these two omegas, then also you will get a discrete probability space. Okay, because this is a countable infinite. And in that case, every outcome is a pair in the form A comma B, where A is from the first set and B is from the second set. Okay, and in this case, when you try to assign the probabilities, you will take the singleton event, which is nothing but in the form of every singleton event will only have one outcome A comma B. So you assign the probabilities to this, right? So this probability would be a function of A comma B. Every unique pair A comma B, you will have a number, right? So it's a two-dimensional sequences or a function which depends on two parameters, right? So if you define this, you will get the probabilities for each singleton events, and using the same formula, then you can extend it to every possible element of the sigma algebra by adding all probabilities of all events which makes this event you have taken.